Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Today, our group 5, we present on Reactor Types 2, downstream processes, collecting, analyzing, and reporting data. The group's members are ADILA 1192476, SYAZWANI 1192456, myself AFIFAH 1192470, UMAIR 1192459, and NURUL IZZAH 1192455. In this video, we present on downstream process, which is the introduction, ammonia synthesis, methanol synthesis, Fischer-Tropsch synthesis, and collecting, analyzing, and reporting data.
Downstream process.
Today, I want to talk to you about downstream process. Downstream process refers to the recovery and purification of biosynthetic product, particularly pharmaceutical, from natural sources such as animals, plant tissue, and fermentation routes, including the recycling of salvageable components and the proper treatment and disposal of waste. There are three types of downstream process. First, ammonia synthesis. Second, methanol synthesis. And the last one, Fischer-Tropsch synthesis.
Ammonia synthesis.
Ammonia synthesis. Ammonia synthesis is the world's second largest manufactured industrial chemical. Ammonia production is the most complicated process, involving the greatest percentage of catalytic steps and 4 chemicals, involving the ammonia, methanol, hydrogen, and carbon monoxide that depend on the related syngas process for their development. Ammonia is most essential chemical substances globally, and 88% of it is used as the fertilizer for the food production. What is ammonia synthesis? Ammonia synthesis from nitrogen and hydrogen, which is involved in Haber process. Haber process is one of the few industrial processes where an unsupported metal catalyst is mostly used. As we know, ammonia is the base chemical for nitrogen fertilizer, explosive industry, refrigerant gas, for purification of water supplies, the manufacture of plastics, explosives, textiles, pesticides, and dyes. We go to the production history. In the year 1904, the Haber entry into the field of nitrogen fixation to investigate conditions for a combination of atmospheric nitrogen with oxygen using the electric arc, or directly with hydrogen to avoid ammonia. By the year of 1905, Bicklin or Ike succeeded in producing the calcium nitrate from the air. And in the year 1906, Nurse claimed that Haber reported 0.005% yield of ammonia. And finally, in 1913, the Haber or Bosch process was developed. That we know. Until now, we use mostly this process in many industry fields. The Haber process is used in manufacturing of ammonia from the nitrogen and hydrogen. The process combines the nitrogen from the air with hydrogen derived mainly from the natural gas such as methane into the ammonia. The reaction is the reversible reaction, and this is the exothermic reaction. General condition of the process. There are three main parts in the general condition of the Haber process. First, the catalyst. The catalyst is actually slightly more complicated than the pure ion. It has the potassium hydroxide added to it as the promoter and a substance that will increase its efficiency. And the second one, the pressure. The pressure varies from one manufacturing plant to another, but is always high. And the third one, recycling. At each pass of the gases through the reactor, only about 15% of the nitrogen and hydrogen are converted into the ammonia. This figure also varies from plant to plant. By continual recycling of the unreacted nitrogen and hydrogen, the overall conversion is about 98%. And as we know, the ideal ratio for the hydrogen and nitrogen is ratio 1 volume of nitrogen to the 3 volume of the hydrogen. The steam reforming is suitable reforming process due to the high of hydrogen and carbon monoxide ratio. It is combined with an air balloon ATR that introduces by the nitrogen gas, and the equilibrium is limited, and it is due to the high pressure which is ranged between 100 until 250 bar, and low temperature which is 675 Kelvin until 770 Kelvin. There are low single pass conversion which make the recycling necessary. And last one, carbon monoxide and carbon dioxide has to be removed prior to the ammonia synthesis, which is involved in the several extra process units.
I will continue on ammonia synthesis. This is Haber-Bosch plant figure. Here we can see the primary reformer, air feed, secondary reformer, carbon monoxide conversion, washing tower, ammonia reactor, heat exchanger, and ammonia condenser. Depending on its origin, the synthesis gas must first be freed from impurities such as hydrogen sulfide or organic sulfur compounds, which act as a catalyst poison. High concentrations of hydrogen sulfide, which occur in synthesis gas from carbonization coke, are removed in a wet cleaning stage such as solvent process, while low concentrations are removed by adsorption on activated carbon. Organosulfur compounds are separated by Fraser's ring adsorption together with carbon dioxide after carbon monoxide at conversion. A typical modern ammonia-producing plant first converts natural gas, liquefied petroleum gas, or petroleum naphtha into gaseous hydrogen. The method for producing hydrogen from hydrocarbons is known as steam reforming. The hydrogen is then combined with nitrogen to produce ammonia via the Haber-Bosch process. Starting with a natural gas methane feedstock, the different steps used in the process of producing hydrogen. The first step in the process is to remove sulfur compounds from the feedstock because sulfur deactivates the catalyst used in subsequent steps. Sulfur removal requires catalytic hydrogenation to convert sulfur compounds in the feedbacks to gaseous hydrogen sulfide. The gaseous hydrogen is then adsorbed and removed by passing it through beds of zinc oxide, where it is converted to solid zinc sulfide. Catalytic steam reforming of the sulfur-free feedstock is then used to form hydrogen plus carbon monoxide. The next step then uses catalytic shift conversion to convert the carbon monoxide to carbon dioxide and more hydrogen. The carbon dioxide is then removed either by absorption in aqueous ethanolamine solutions or by adsorption in Fraser's ring adsorbers (PSA) using proprietary solid absorption media. The final step in producing the hydrogen is to use catalytic methanation to remove any small and residual amount of carbon monoxide or carbon dioxide from the hydrogen. To produce the desired end product ammonia, the hydrogen is then catalytically reacted with nitrogen derived from processed air to form anhydrous liquid ammonia. This step is known as the ammonia synthesis loop, also referred to as Haber-Bosch process. Next is about ammonia converter. Here is two cases about ammonia converter. In figure 1 shows the overall layout of an intercooled horizontal ammonia converter. The feed after entering the reactor passes through the shell of the internal heat exchanger where its temperature rises. When the gas passes the first bed and the reaction takes place, its temperature increases and it then enters the tubes of the heat exchanger to cool down. No specific operation is carried out between the second and third bed. On the second case, the horizontal ammonia converter with two quench flows is illustrated in figure 2. The reactor inlet gas is divided into three parts: mainstream, first quench flow, and second quench flow. The mainstream passes through an empty space of beds and the reactor wall and goes to the internal heat exchanger where it is heated with the output product stream. In the heat exchanger, the gas preheats to about 400 degrees Celsius and then enters the first bed. After passing through the first bed, the temperature is increased to about 469 degrees Celsius. The output gas from the first bed is quenched with the first quench flow and consequently its temperature is decreased. After that, it is sent into the second bed. Similarly, the output gas from the second bed is mixed with the second quench flow and it is entered to the third bed. Finally, the product gas from the third bed is directed out of the converter through the heat exchanger. During the first few years of the 21st century, many improvements were made in ammonia plant technology that allow existing plants to increase production rates and new plants to be built with larger and larger capacities. Competition between technology suppliers is quite fierce. Three technology licenses, KBR, Kellogg Brown and Wood, Holder Topsoe, and ThyssenKrupp Industrial Solutions (TKIS) currently dominate the market. The modern ammonia plants designed by KBR employ its proprietary purifier design, while Holder Topsoe offers as an ammonia plant design that has a proprietary side-fixed reformer in which radiant burners supply heat for the reforming reaction. And for the ThyssenKrupp's dual pressure synthesis loop, design features a one-stroke reactor between syngas compressor. That's all for ammonia synthesis. Next, we will go on another synthesis, which we will present of our group's member.
Methanol synthesis.
Okay, my name is NURUL binti ZULKIFLEE and my matrix number is 1192455. We will continue with methanol synthesis, which it is a process to produce the methanol. And methanol is a base chemical for formaldehyde and also acetic acid. The production of methanol is really important as it is utilized as a fuel, solvent, energy storage medium, and also as a feedstock in the industry. There are three steps in the production of the methanol via synthesis gas, which are the production of synthesis gas, conversion of synthesis gas, and also the distillation of reactor effluent. Nowadays, the process is done by using the copper-based catalyst gas. Okay, next is the production history. Okay, the first production occurred in 1923 by British Aniline and Soda Fabric (BASF), and in 1960 the old process is replaced when the ability to produce sulfur-free synthesis gas made it possible to use more active copper-based catalyst, and this process is operated in a low pressure, which is 60 to 80 bar, and in a low temperature, which is 200 to 250 degrees Celsius. And since then, the production of methanol occurred in a two low pressure process, which is ICI and Lurgy process. And next, this is the chemical equation of the methanol synthesis. Okay, so the ideal for H2 and CO ratio is 2, and it is a low single pass conversion where recycling is necessary, and equilibrium is limited as it is a high pressure
which is 50 to 100 bar, with a lower temperature, which it is around 500 to 550 Kelvin, and the temperature for this process is below than 570 Kelvin due to the catalyst sintering. Okay, the catalysts have to be very selective, because the methanol is thermodynamically less stable than the methane. So the catalyst that we usually use is copper, zinc oxide, and also aluminium oxide. Next is the reactor, ICI reactor. Okay, for this reactor, 40% of the feed will enter the reactor, and another 60% of the feed is for the quench. And then there are separate part where the gas and liquid will be separated after several cooling process. And lastly, there are distillation part where there are two columns. In the column first, we have the gas and the light impurities will be removed, and for the column second, the methanol will be separated from the alcohol, the heavy alcohol, and also water.
A flow diagram presenting the ICI low-pressure methanol synthesis.
My name is SAHIRA ADILA MARZUKI 119247. So for my part, I will continue to present about methanol synthesis. Lurgi reactor is a reactor for methanol synthesis. For your information, Lurgi megamethanol is one of type of Lurgi reactor. It can generate methanol on a large scale. It switches to large scale production. It converts syngas derived from any carbonaceous feedstock into raw methanol using a two-step process. This reliable technology offers minimized production costs at maximized capacity. Next reactor for methanol synthesis is Haldor-Topsoe reactor concept. Haldor-Topsoe is a global leader in the supply of catalysts, technology, and services to the chemical and refining industries. Topsoe aims to be the global leader within carbon emission reduction technologies by 2024. By using Haldor-Topsoe reactor concept, we can produce e-methanol. E-methanol is considered promising low carbon transportation force and energy carrier, so it is good for our environment. The last reactor for methanol synthesis is slurry reactor fluidized bed. What is fluidized bed? Fluidized bed is a physical phenomenon occurring when a quantity of a solid particulate substance is placed under appropriate condition to cause a solid or fluid mixture to behave as a fluid. The resulting phenomenon is called fluidization. So if you want to know more about slurry reactor, you can watch the last week presentation. So in a slurry reactor, a solid catalyst is suspended in an inert hydrocarbon liquid. It undergoes exothermic reaction or absorb heat. It occurs in uniform temperature. Temperature control is essential because it has a large effect on the selectivity of the catalyst toward desired product. The catalyst that been used is solid such as copper oxide, zinc oxide, and aluminum oxide. So the advantages for using a slurry reactor is higher single pass conversion. With higher single pass conversion, we are able to achieve high purity product and less compression costs. We have other method for methanol synthesis, which is direct conversion of methane. Pathway for direct conversion of methane to methanol is via partial oxidation of methane over a metal containing zeolite catalyst. This method actually highly efficient with no carbon dioxide production, but in a very low yields of product.
Fischer-Tropsch synthesis.
Before we move to long explanation about Fischer-Tropsch synthesis, I want to tell about its history. In 1923, Fischer or Tropsch converted synthesis gas into a wide range of hydrocarbon and or alcohol. During World War II, Germany applied Fischer-Tropsch synthesis to make fuels. And lastly, in 1950, South Africa started to make fuels and base chemicals in Fischer-Tropsch plants to reduce the dependence on imported oil. So the application of Fischer-Tropsch synthesis in fuels and wax production.
Assalamualaikum warahmatullahi wabarakatuh. My name is UMAIR. My material number is 1192459, and I will present to you the Fischer-Tropsch synthesis, or we call it as FT synthesis. FT synthesis is a catalytic chemical reaction of syngas, which are synthesis gas. The example is carbon monoxide and hydrogen, CO and H2, react and will produce converted hydrocarbon. As you can see here, the chemical equation, which are CO plus 2 hydrogen, will resulting into the alkene hydrocarbon and the water. So for this reaction in catalyst, and a certain temperature and pressure. For the certain temperature and pressure which is 250 Celsius and 5 to 10 atmosphere for the reaction to occur. But then the example of the catalyst is considered as a traditional metal of the cobalt, iron, nickel, and ruthenium. So these are the reactor for the FT synthesis. So moving to the next part. So now we move on into the second part of the FT synthesis, which is steps in FT synthesis. There are two steps, which are production of synthesis gas and the hydrogenation of the synthesis gas. For the first step is syngas is obtained from the coal or biomass product. As you can see here, the example of the starting item of the synthesis gas, which are gas, oil, coal, and biomass. Then the coal is react with steam and produce water gas. This steam performing will produce the water gas, and then water gas is react with hydrogen gas to obtain the synthesis gas, which is carbon monoxide and hydrogen. Then for the second step, which is hydrogenation of the synthesis gas. The synthesis gas is then hydrogenated to gain alkene, and this alkene will transform into the desired product, which is in the FT synthesis is the synthetic lubricant oil and the synthetic fuel. Okay, that's all for the FT synthesis. Now we move on into the data analysis. And now for the collecting, analyzing, and reporting data. So first, the purposes of the collecting data, which is the first purpose is to know activity, selectivity, and live data for the catalyst selection, which are we need to know the selectivity of chosen catalyst that we use in a certain reaction or certain reactor. So for the second one is the chemical reaction mechanistic and kinetic data for understanding the reaction at a fundamental level, modeling the reaction process and or designing the reactors, which means that we need to understand the chemical reaction and reactor design of the synthesis. Okay, then and for the third point, which is the process variable data over wide range of condition for purposes of designing large-scale reactor, experimentally validating models and optimizing the catalytic process, which is that we need to process the variable data in terms of the condition, which are example of temperature, maybe pressure, for we to know for we to know and validate the models and optimize the catalyst that we use in this process. Okay, now for the next part, which is the step of collecting and analyzing data. which is first, we have 3 steps. For the first step is the selection of reaction and catalyst. Second step is the selection of reactor type, and the last step is analysis of data. As you can see in the diagram, first we need to select the reaction and catalyst that we want, or we want to use, or we want to study. And then we need to find the reactor and condition and all the criteria that will fit our reaction and catalyst. After we done experiment, we need to collect all the data, and we need to do the data analysis, which are integral, differential, and initial rates of the data that we found. After that, we will find the result that we want, which is a mechanism of the experiment, rate aspiration, and the process of optimization of the catalyst that we use. Okay, done for the steps. For the step part, now we move on into the. And now we discuss how to analyze the experiment. First, we need to analyze the rate of data, which is objective. First objective is to find the rate of the equation of our experiment. And the second one is to determine the catalyst activity, selectivity, and activity stability, which means that we need to study our catalyst. And for the third part is determine the effect of important process variables such as temperature, pressure, reactant concentration, and space velocity on activity, selectivity, and stability. Also, we need to find the significant or relationship of our important process with this important process variable with this experiment. Okay, for the last part, the extracting rate constant and concentration dependency is in the integral analysis and the differential analysis. Okay, that's all from me. Thank you very much.
Thank you, Dealis, for watching. Good luck.